This is a clip where questions are asked to today's physicists. Of course, you are welcome to ask your own and do so in the comments section. They may be included in a future clip. I play the role of the physicists and therefore do not completely agree with probably many of the answers. With me are all people I've talked to in the past and read, and among others, ChatGPT. How does the structure of the universe come about? The physicist. From the beginning, we call the Big Bang, space-time expands and holds a lot of energy. This energy is not distributed evenly as the cosmic microwave background shows. The energy is contracted towards certain what we call filaments in space by the distribution of mainly dark matter. In these places, galaxies form because gravity pulls matter together. What is dark matter? The physicists. We are not sure yet, but a number of existing or unknown elementary particles are considered as dark matter candidates. While its exact composition is unknown, dark matter is generally believed to consist of some form of exotic non-baryonic matter that does not interact with electromagnetic forces such as light. Its presence is inferred through its gravitational effects on visible matter and light. What are these elementary particles made of? The physicists. We have no knowledge about that. That is why we call them elementary. They have no further known substructure. They are outcomes of expressions of symmetries of nature, like their colleague elementary particles. Are we looking for what they are made of? The physicists. We currently suspect they are made of string stuff, but that is still speculative. The mathematics is promising. In general, instead of asking about their internal structure, we can inquire about their properties, behaviors, and interactions with the framework of fundamental forces and fields. What is gravity? The physicist. Since 1915, when Einstein gave us general relativity, our best theory is that gravity is an expression of moving energy and deforming space-time. Gravity is no longer a force. Energy shapes space-time and moves according to the shape of space-time. What forces are there? The physicists. We have electromagnetism, the strong force, binds quarks together to form protons, neutrons and other hadrons, and it's also responsible for holding atomic nuclei together. And the weak force, responsible for certain types of nuclear decay processes. And we consider gravity to be the fourth force in classical mechanics. In our models for the small world, for quantum mechanics and quantum field theory, gravity doesn't play a role. In string theory, gravity is a force and modeled as a spin 2 particle called the graviton. In the standard model of particle physics, the 3+1 forces are modeled as bosons, elementary particles. We have the photon, the W and Z, the gluon and the graviton. Photon, W, Z and gluon have spin 1. The graviton is supposed to have spin 2, but we have not yet experimentally found or confirmed the existence of gravitons. We suspect that all forces can be unified as being of the same nature. What are outstanding problems in physics? The physicists. The most problematic and important is to make this theory for the really large, the cosmological structures, namely general relativity, to combine it with the theory of the really small, namely quantum field theory. We call this quantum gravity. Furthermore, we do not know what dark energy and dark matter are, and we would like to know more about the beginning and evolution of our universe and black holes, quantum information and computing, particle physics beyond the Standard Model, and lots more. When do you say something is not considered physics? The physicist. In general, something is not considered physics when it does not fall within the scope of the principles, the theories and methodologies that are traditionally associated with the field of physics. Physics is a broad and diverse discipline that deals with the study of matter, energy, space and time, as well as the fundamental forces and interactions that govern the universe. Here are some criteria that help delineate what is considered physics. The subject matter, the theoretical framework, mathematical models, theories, principles, empirical observations, evidence and reasoning. Experimental verification, quantitative analysis, and types of applications. If a topic or subject matter does not align with these criteria or does not involve the study of physical phenomena using the methods and principles in physics, it is typically not considered part of the discipline of physics. However, it's worth noting that the boundaries between scientific disciplines can be fluid, and interdisciplinary research often bridges multiple fields to address complex scientific questions. When do you consider new physics to be appropriate? The physicist. New physics is considered appropriate when there are compelling reasons to believe that our current understanding of the universe is incomplete or inadequate to explain observed phenomena. The exploration of new physics involves theoretical speculation, experimental verification, and the continuous refinement of our understanding of the fundamental laws of nature. For instance, when we have experimental anomalies, unexplained phenomena, theoretical inconsistencies, missing fundamental understanding, or theoretical extensions like supersymmetry. What if you doubt, for instance, the mathematical foundations because certain definitions seem incorrect? For instance, the definition for number, because you cannot always add one. The physicist. This is a difficult subject. Philosophers, logicians, and mathematicians are discussing the foundational issues. Often words like practical, theoretical, conceptual, boundedness, limitless, and in principle are used when trying to define subjects like number, infinity, and continuity. The two worlds of reality and the abstract world are in the process of being compared. Often arguments are suggested where mathematics is not in the real world. Should we describe nature using laws or using properties? The physicist. The properties of nature are inherent characteristics or attributes of objects, substances, or systems in nature. These properties include observable features such as mass, charge, temperature, and density. They are fundamental aspects of the natural world and exist independently of human observation or interpretation. The laws of nature are general principles or regularities that describe the behavior of natural phenomena. These laws are formulated based on empirical observations, experimental data, and mathematical models. They codify the relationships and patterns observed among properties of natural systems. Now, let's examine the relationship between properties and laws. Properties as foundations serve as the foundation upon which laws of nature are formulated. Observations of properties lead to the identification of regularities and patterns, which are then codified into laws. In this sense, properties exist independently of laws and provide the empirical basis for understanding natural phenomena. The influence of laws. While properties themselves do not depend on the laws of nature, they play a crucial role in shaping our understanding of these laws. The relationships and patterns observed among properties guide the formulation and inference of laws. Laws are derived from observations of how properties interact and behave under different conditions. Human perspectives and interpretations of laws are indeed influenced by our observations and understanding of properties. The properties of nature provide the empirical basis for formulating and testing laws, and our interpretations of laws are informed by our observations of properties. However, once formulated, laws provide a framework for understanding and predicting the behavior of natural systems, which may in turn lead to further observations and discoveries regarding properties. Properties shape our understanding of laws, while laws provide a framework for interpreting and predicting the behavior of natural systems, ultimately contributing to our understanding of the natural world. Can there be a two-layer paradigm where in one layer there is just reality based on one substance, and in another layer there is the perspective of perceived objects, like a human perspective or a measuring apparatus perspective? The physicist: my first answer is yes, and the scientific method is in the first layer. But here's my adjusted answer. The answer is still yes. Considering the inherent subjectivity and perspective involved in scientific observation and measurement, it's reasonable to argue that the scientific method falls within the second layer, which represents subjective perspectives or interpretations, rather than solely within the first layer of objective reality. While the scientific method is rooted in the objective study of the natural world and aims to uncover objective truth about reality, it relies on human observation, interpretation, and judgment at various stages of the process. These subjective elements introduce a degree of uncertainty and perspective into scientific inquiry. Key aspects of the scientific method that fall within the second layer include observation and measurement. Scientists use measuring instruments and observation techniques to gather empirical data about the natural world. However, the act of observation involves subjective perception and interpretation, influenced by factors such as human biases, perceptual limitations, and experimental conditions. Hypothesis formulation and testing. Scientists formulate hypotheses based on observations and existing knowledge, but the selection and formulation of hypotheses can be influenced by subjective factors such as intuition, creativity, and prior beliefs. Hypotheses are then tested through experimentation and observation, where subjective judgment may come into play in the design and interpretation of experiments. Interpretation of results. The interpretation of experimental results involves subjective judgments and inference, as scientists analyze data and draw conclusions about the underlying mechanisms or phenomena being studied. Different scientists may interpret the same set of data differently, leading to diverse perspectives and interpretations. Peer review and consensus building. Scientific findings undergo scrutiny through peer review and validation processes, where the subjective judgment of experts plays a crucial role in evaluating the quality and validity of research. Consensus building within a scientific community involves negotiation and persuasion among individuals with diverse perspectives and interpretations. Overall, while the scientific method is grounded in the objective study of reality, it operates within the context of subjective human perspectives, interpretations, and limitations. This acknowledgement of subjectivity underscores the importance of critical thinking, skepticism, and rigorous methodology in scientific inquiry.